A of x be any ideal? Right, so if I take an element in I, then it looks like, f, so it looks like a n x to the n plus a n minus 1 x to the n minus 1 plus a1x plus a naught. Right, so define J sub n to be the set of all an in A such that an is the leading term of some f in I and degree f equals n. Okay, so if you want to prove anything about the polynomial ring, then you're going to be taking your polynomial and writing him out basically as a little sequence of elements of A according to some rules of manipulation. Right? And so, for some purposes, we want to think of this, there are lots of different ways of thinking of a polynomial, but one way of thinking of it is just a sequence of these n plus 1 coefficients. Right? So if the guy is of degree n, he has a leading coefficient. So we look at this leading coefficient. Right, so Jn is an ideal. And Jn is contained in Jn plus 1. Okay, so these are things that we can easily argue about. We can easily see why this is true. So if I've got an and bn, the coefficients of f and g degree n, right? Then I can do an plus or minus bn is coefficient of f plus or minus g. And when I'm talking about the leading coefficient, there are no terms of higher degree in here, so I do f plus or minus g, and they have the highest term an plus bn. Right? So if that's 0, I'm also happy. I could maybe say an equals 0, or an is a leading coefficient. Right? And then so if I do, if I've got, so a times an is also in Jn, right? Because I can do a times f, right? For all a in A. Okay, and to see that Jn is contained in Jn plus 1, well, this I here is supposed to be an ideal in there, and so he's supposed to be, if I do I times x, if I do f times x, then he's still contained in I. So let me just continue. Okay, let me. Moreover, an in Jn implies implies f equals an plus is in I, and then x times f is an x n plus 1 plus and so on is also in I. Right. So here we're actually using the rule for multiplying polynomials. We're using it in rather a trivial way, but we're still using it. Oh dear. Okay, so I'm assuming that A is Noetherian and Jn is contained in A, and Jn is contained in Jn plus 1. Right? And so this is exactly an ascending chain. Right? And this means that, so there exists some m so that Jn equals Jm for all n greater than m. Or let me say n naught for all n greater than n naught. Right? So this is an increasing chain of ideals. It increases a bit, increases a bit, increases a bit. But the ring is Noetherian, and so at some point that increasing has to stop. So now I'm going to try to show you that therefore the original ideal I in AX is finitely generated as an ideal in AX. Right, so each Jn individually in A is finitely generated. So, you know, this is going to get messy, but let me write Jn is, you know, Fin I equals, you know, 1 up to Kn or something. So for each of these ideals Jn, I can find some finite number, you know, F1 up to Fk, of elements in Jn, so that Jn is this finitely generated ideal. So I do this for n equals 0, 1, up to n 0. Right, so I get a bunch of guys here called Fin, right, where n is 0 up to n 0, and I is 1 up to Kn. And so, oh, I'm sorry. I've made a small boo-boo. I've made a small mistake. So, I'm sorry. So, yeah, I'm sorry. This is AIN. So I will, and so each AIN is the leading term. This is just by construction of Jn. Each of Fin equals, you know, AIN, leading coefficient of a term x to the n plus and so on, with this in Ix, in I. Okay, just to say where we are. I is some ideal in the bigger ring, the polynomial ring over A. Right? So this ideal Jn is formed by all the elements in the initial ring A, in the first ring A here, not the bigger ring, which are leading coefficients, which are the first order term. So here I'm saying the Jn is finitely generated, so Jn is generated by some finite set of elements. For each one of these elements, he's a leading coefficient of something. So I take that something, right? And then I'm going to look at all of these guys. So all the Fin are in I, and between they give between them and between them they provide all the leading terms of all the elements of I. Right, so these fin, they're all of degree less than or equal to n0. So at every stage of this tower, at every stage of this increasing chain of ideals, I choose finitely many of the elements, and then when I get to n0, I just stop. Right, and so now if G is in I, then G has some leading term. So G is A, maybe some n, x to the n, plus lower order terms. Right? And what can we say about this leading term? So this A, if n, sorry. So there are two slightly different things to say, but they're basically the same idea. If n is greater than n0, right, then I say I say that an is in J little n0, and so that's because this an is in. So it's initially an is in J sub n, but we're at the place where the ascending chain has stopped ascending. Right, we've got to the top of the, and so this is Jn n0. Right, and so there exists some combination some linear combination of these elements f I n 0 such that are with the same leading term. So maybe this is sigma b I f I n 0 for I equals 0 up to this number k n 0. Right? And this has the same leading term an. And so then if I do x to the n minus n0 times this same thing, this is a polynomial of degree n with leading term an n x to the n. Right, and so this just means this. So now what I'm going to do is I'm going to do the g minus this x to the n minus n0 times this linear combination. Right, and what I've done is I've killed the top term. Right, this kills the leading coefficient. So G has degree at most n minus 1. Right, and so now I do an induction on this n. So this n goes down and this argument continues as long as n is greater than n0. And then when I get to n0, I just use the same argument, but without this little multiplication term here with so if n is less than or equal to n0, I use the same argument. With f I n I I in I equals 1 up to whatever it is, k sub n. So we're trying to work with these polynomials, and the main thing a polynomial has is an expression as a sum of powers of x, as a linear combination of the powers of x, right? So here it's convenient to choose the highest power and to say, well, if I want to prove something about f and g, then I'm going to be, maybe taking a multiple of f and subtracting off a multiple of g and so on. You do this in lots and lots of different arguments, kind of Gaussian elimination arguments. So here we're doing it systematically to say that we introduce these intermediate ideals Jn, right? And these Jn provide the leading terms for all polynomials in I. And then it turns out that actually we only need finitely many of them by using the ascending chain condition. And so then I can take my G and I can guarantee by subtracting off the finitely many given elements, linear combinations of the finitely many linear given elements, I can guarantee to reduce the degree. So I reduce the degree, eventually I get to degree 0, and then eventually I get to degree -1. So there's no problem about the induction starting here. Okay, so look, the problem with this algebra is that it takes us a very long way away from the geometry. So why exactly I need this? I want to write down x is v of I in an, and I want this to be v of f1 up to fm in an. This is the set of points p is a1 up to an, such that fi of p is 0 for all I. Okay, so I'm going to do this in several different ways, but so the slogan, algebraic geometry, is the study of locuses defined by polynomial equations. Right, so the primitive definition of an algebraic variety is I start off with this space. Remember, this space is just the same thing as Kn. So it's a set of n-tuples of elements in the field. And then I ask for simultaneous zeros of finitely many polynomials. So, it's the same game that we play in school maths with quadratic equations, and we play in university maths when we're doing Galois theory. I've got some polynomials, and I'm looking for the roots of the polynomials. But here I'm looking for simultaneous roots of several polynomials. Right? So, this is a slogan. It's the thing we're going to study are these algebraic varieties. And it's very convenient when I've got this f1 up to fm to forget them and remember the ideal. But I need to know the ideal is finitely generated. There are many different places where I need that the ideal is finitely generated. So that's why we have to do this strange, algebraic rigmarole, strange procedures in algebra. Okay, any questions? Any problems? So I'll be producing another homework sheet on Thursday's lecture, and you're supposed to hand in your homework on Thursday. Then there'll be a break in lectures for a week.